Okay, there we go. You should be able to see that now.
Yeah, yeah.
Brilliant. Okay, so this is our last topic that we're going to cover within the fundamentals of chemistry module. Okay, so you'll be happy to know. So it's all just about to do with the rate of reactions. Okay, so I kind of touched on this a little bit last week when we were talking about the chemical equilibrium and what can affect certain rates of reaction. So we're just going to go a little bit in depth of what a rate of reaction actually is, some of the calculations that are involved in the calculation of the rate of the reaction, and then what can affect the rate of the reaction. Okay, so let's start it here. Oh, sorry now. Okay, so what the rate of reaction actually is, okay, so it's defined as the change in concentration of any species that are involved in the reaction itself. So we can either monitor the reactant or the product here, and you divide that by the time it takes for that change to occur. So you'll see here in this kind of common enough example, all right? If we were to look at A, so the reagents there, okay, so this kind of line that's decreasing over time, at the beginning of the reaction, we're going to have lots of our reactant, okay, because it obviously hasn't reacted yet. It's at the very, very start of the reaction. So over time, that once we start reacting those reagents together, the reagents will start to decrease in concentration. Okay, so that's what we see here. And just at the end of the reaction time, then we should have nearly a zero concentration of our reagents left over. Okay, which would be expected because our products that are forming at the same time, so our B there, will start increasing over time up until a certain point where we can't form any more B because we've run out of our reagents. All right. So what the rate of reaction actually looks at then is how the concentration of either your reagents or your products change over time. So, for example, if I were to look at the concentration of the reagents I have at the very start, oh, sorry, concentration of reagents I have at the very start over here, and if I compare it to the concentration that I have left over at the very, very end of that reaction, my rate is how they changed over that time. All right. And the very same thing can be said for my product formation. So obviously at the very start, I start with 0% or zero product because it hasn't formed yet. Over the course of that reaction, that's going to keep forming and forming until a certain point where no more can form. And then I look at the change in concentration that happened over the reaction time. All right. Is that okay with everyone so far?
Yeah.
Okay. So we can look at what's called the average reaction rate. Okay. So the rate of formation of a product, so in this case, it's our B there, or destruction, or the way we use up a reactant. Okay. So our A, we can calculate the average reaction rate. So how long did it take in total for that concentration to change? All right. So I did this quick little example here. All right. So say if a question asked you that at the end of a reaction, okay, so I'm talking about up here. So I'll just change that into so I'm talking at the end of the reaction here. All right. So say for example, if 5 moles of product formed at the end of the reaction and the reaction took 120 seconds in total. Okay. So if you can picture this graph went from 0 to 120 seconds. And then at the end, 5 moles of product formed. All right. What would be the average rate of reaction? So what you'd look at there, okay, is that you take the concentration at the end of the reaction. So in this case, I'm talking about here, which would be 5 moles. All right. You then take, so you're looking for the change, you're looking to see how that concentration changed over time. So you take your value at the end there and you take away the value at the very start. Okay, so because it's a product, there's no product at the start. So that's why I have a 0 moles over here because the reaction hasn't happened yet. Then you divide that then by the total time of the reaction. Okay, so in this case, the reaction proceeded for 120 seconds. So that's what your time would be over here. And your starting time is obviously 0 seconds. Okay, because you're beginning the reaction at that very moment in time. So you say it's 0 seconds. So that kind of tidies up to your 5 moles, okay? So your concentration that you have at the end, minus your 0 moles, because that's what you started out with. And then the total course of the reaction then lasted 120 seconds. and you take away the starting time of 0 seconds. So obviously that's going to be 120. And then just dividing that one by the other to give you a rate of 0.042 moles per second. And what that actually means then is that 0.042 moles of product formed every second of that reaction. Okay, so that's on average, that's how many moles of product you were forming per second. Is that okay with everyone, guys?
Yeah.
Perfect. So that's your average reaction rate. So you're looking almost as a snapshot of the whole reaction itself. So what we're going to look at now is what's called the instantaneous rate. But just for now, the average reaction rate is a snapshot of your reaction. So it's just how much changed over the total course of the reaction. If we wanted to look a little bit more in depth of the reaction, so we could look at the instantaneous rate. What the instantaneous rate of reaction means is just the reaction rate at a very particular moment in time during that reaction. Because as you'll notice, okay, the rate of a reaction constantly changes throughout it, okay? So if I were to just focus on this little bit of the graph at the minute, all right, so this is the exact same example that I have here, but I'm just looking at the very, very start of that. So at the beginning of the reaction, the initial rate of the reaction is very high, okay? So what you'd notice is that those lines are very, very steep. So the steeper the line, the faster the rate of the reaction, okay? So it's the faster your reactants or your A value there is being used up, or the rate B is forming is very, very steep. Okay, so it's happening very, very quickly here. The reason for that is because we have a very high concentration of A that's available to collide with one another to form the products. So if you think about it, at the very, very start of the reaction, there's an awful lot of reactant there that are able to react and form B. So that's why you see a very fast or very steep rate of reaction at the start. If I were to drag that reaction on then, so if we were to look at kind of the midway point of the reaction, the rate of the reaction begins to decrease. Okay, so what I've said here is that the lines drawn on the graph become less steep. So you'll notice that, okay, so towards the start of the reaction, they're very, very steep. Towards the middle of the reaction, they almost start to level off or plateau, okay, or it's not as steep as it was at the very start. The reason for that is that the reactants are being used up. Okay, so we had a very high concentration at the start. Then over time, the reactant concentration starts to decrease. Okay, so there's not as much reactant available to react to form B. So the formation of B is starting to level off as well. Okay, so it started off very, very quickly, but because we don't have a lot of reactant left over, it's starting to level off. So no more B or products will start to form. Then towards the very end of your reaction there, you'll see almost very little to no change. Okay, so you'll notice that there, even just going from the middle, that it almost starts to plateau off. All right. The reason for that is because there's no more reactant left. Okay, so you'll notice there the concentration is decreasing throughout the reaction. And then towards the end, there's very, very little change because it's almost reached 0. All right. So essentially all of your reactants have been used up and converted into your product. If you look at your product, okay, so it started off forming very, very quickly, started to plateau somewhere in the middle, and then it will level off completely because no more product can form because you have no more reactant left over. So at that point of the reaction is when you stop it, okay, because the reaction won't continue, you have no reactants left over, so no more product will form. And that's when you stop the reaction, okay? Does anyone have any questions on that so far? No? All good so far?
No.
Okay. So this is what I mean is like the rate of the chemical reaction is constantly changing, okay? So it's good to get the average rate. So if I go back just here. So an average rate will give you an estimation of how much is forming per second, okay? So it's always a good value to have because it's an estimation of how quickly the reaction is proceeding. The instantaneous rate will give you a more accurate value of certain stages in the reaction. Okay, so it'll almost give you if you wanted to get, say, your initial rate at the very start, we can calculate that, and that would be much faster than your average because that's taken everything into account, whereas your instantaneous rate is only taken a very specific time point into account. So we'll normally the exam questions, they will ask you both. Okay, so they'll ask you to calculate the average, and then they might give you a time point, and they'll say, well, calculate the instantaneous rate of the reaction based on that time. All right. So we'll do a couple of examples of those in a second. So the instantaneous rate of the reaction. So like I was just saying, you can calculate the specific rate of the reaction at a particular time. Okay, so at a particular time across that entire reaction. So what I like to do is I think of it like a car journey. Okay, so say for example, you had an hour-long car journey and you were traveling an average of 80 kilometers an hour. Okay, so that would be your average speed over that whole hour-long car journey. Where the instantaneous rate of reaction comes into play is that, well, it was 80 kilometers an hour over an hour, but it didn't take into account that you slowed down at a roadwork sign at say 20 minutes, so your speed decreased, or if you sped up to join a motorway, for example. So even though you're kind of slowing down and increasing your speed across the entire car journey, your average was only 80 kilometers an hour. But we can apply the same principle here. So we can calculate an average rate of reaction, whatever that might be, but we can look at certain time points in the reaction to see, well, was it increased at a certain point or decreased at a certain point? Okay. So how we actually do that then, and I will say quite important, just putting that out there. So you can calculate the instantaneous rate of reaction, okay, basically by drawing a graph. Okay, so I'll go through examples of this in a second because it will kind of come into more focus once I do an example out. But the kind of main points that you'd want to do here is that you'll be given a concentration, a list of concentrations. Okay, so you'll be given data, and then you'll be given the corresponding time for that data. Okay, what you do is you plot the graph. Okay, so in this case, your concentration is always on the y-axis, and your time, whatever that might be, is always on the x-axis. Okay, so that's very important. Time is always on the x-axis, and your concentration is always on the y-axis. So you'll be given, say, graph paper, you'll draw that out, okay? And then it'll give you a certain time, okay? So we'll say, and I have that example done out in a second, but it will give you a certain time across that reaction to calculate the instantaneous rate, okay? So say, for example, if it's there, you come along and then you draw a tangent line to that point, okay? So similar to what's drawn here. And then you pick 2 points along that tangent line and take note of the concentration. So I have them kind of color coding it down here, okay? So if you put a point on that tangent line up there, that's the concentration at the start of the line. The concentration at the end of the line is somewhere down here, okay? Then you take the corresponding time. So if you took that concentration there, you look down to see what the time was. And again, that will be a certain value. And then the very same thing here is that you have a concentration at the end of the line here, and you drop it down to the time at the end of the line there. Okay, so they correspond with each other there and there. Okay. And then what you have to do to calculate the instantaneous rate of reaction is just take one from the other. Okay. So you'll have a concentration up here. You take away the concentration that you've labeled down here. And the same with the time. Okay, so you have a time here, and then you take away the time at the end of the line there. Does anyone have any questions on that so far? Because I know it's quite general to see it done out like that, but they're the kind of steps, and then I'll go through an example. But does anyone have any questions at this point? No? All good so far?
Yep.
Okay, perfect. So it'll make a little bit more sense when I start doing out examples of it, okay? So a typical exam question would be calculating the instantaneous rate of, say, product formation at 30 seconds, okay? So you'll always be given a time point that you have to look at. So what you'll do is you'll be given, like I said, you'll be given a table that has concentration and time data in it. And all you do is plot the graph. Okay. So again, concentration on your y-axis, time on your x-axis. So what you should end up with there, so you'll see that line, just follow along there, is that you'll have your concentration over time, and very similar to what we just saw, very steep at the start, it will start to level off, and then it will plateau. Okay, so that's what you're expecting to see. So it says, then we have to look at 30 seconds time. Okay, so that's that time there. We'll just say that's 30 seconds, okay? So that will be a point on the graph, somewhere here. All right, so that line will be drawn at 30 seconds. We'll come up to meet it, and then we draw this tangent line in on top of it. Okay, so just where it meets our curve. All right, so your tangent line will be there, your 30-second. So draw a line up to meet that curve, and then draw a tangent line to that. All right, so that blue line there, and then the tangent line. So if we extend that out, okay, so say for example, we pick 2 points along that line, and one of them turned out to be 2.5 moles. So we read that across from the concentration there. Okay, so you pick a point and read it across from there. On this point here, then you have 0.5 moles, so it's just reading it from this point in the graph, what it corresponds to, okay? And then you just look at the time that happens. So say 2.5 moles were formed at 45 seconds and 0.5 moles were formed after 15 seconds. So you'll just kind of correspond those based on what they see vertically, okay? So your point will be there. You extend that down, that'll be 45 seconds. Your 0.5 moles, extend it down to 15 seconds. So then you just input all of that into the calculation itself, okay? So just going back here a second. So we look at the concentration at the start of the line. So this is this value here. So we input that value in here, 2.5 moles. The concentration at the end of the line then, so that is your end of the line over here. So that's going to be 0.5 moles. And then your corresponding times. Okay, so that's going to be 45 seconds for 2.5 moles, here and here. And then your corresponding time for 0.5 moles, so dropping that down, is 15 seconds. Okay. Then that simplifies then. So 2.5 minus 0.5 will give you 2 moles. 45 seconds minus 15 seconds will give you 30 seconds. And then you just divide one by the other. Okay, so at that point then, your instantaneous rate is 0.06 moles per second. So I'll just show you an example or kind of in comparison to your average rate there. So say for example, that was at the very start, we calculated your average rate, okay, so it's 0.042 moles per second. But, sorry, now just going forward again. If we wanted to look at a snapshot of that at 30 seconds, it's obviously faster than our average rate, okay, because it's occurring at the very beginning of that reaction. Okay, so when our graph is at the most steep point. Is that okay, guys? Because I know there's an awful lot in that and it will make more sense when I go through the examples, but does anyone have any questions on that so far?
Saoirse, the line you drew, is it always coming up from the point like a zero?
On the zero, is it where
Yeah,
is that?
and touch the tangent at T1, the one we drew after, like
No, so that will be determined based on the time that you're given, okay? So it'll make more sense when I go through my own example here, but say we're calling T1 there 30 seconds. Okay. So what you would do is that you would go to 30 seconds on your graph and then extend the line up to meet the curve. So say if it's at that point there, then you would draw the tangent to that point.
Okay.
So what I will do is I'll go to the examples of these that I have done like online, but then for our revision classes for the next 2 weeks, I'll go through this in much more detail because it's actually much easier to see when I'm physically drawing it rather than kind of using, shapes and kind of word and things. But It's just so you get the gist of it now, and then I'll go through kind of much more greater examples then in the revision classes.
Great.
Okay, so that's, I promise that's the last of the calculations for that one then. So the last little bit that we have to do, just in terms of the rate of reaction, is looking at the factors that affect the rate of the reaction. Okay. Again, I will highlight, quite important. So in terms of what actually can affect the rate of the reaction, okay, so there's certain experimental conditions that we can do to increase the rate. So this is quite important, particularly if we're trying to maximize product formation. Okay, so, and it's all about in terms of reaction efficiency and kind of cost effectiveness of a reaction. We don't want reactions that will take too long and too much of a reactant concentration. Okay, for obvious reasons, that if we had, batches to kind of prepare and they had to be done within a certain time frame, it's not very feasible to have a rate of reaction that's quite small. So the reaction will happen, but it's occurring at such a slow rate that it's not economically viable. The same way that we want to keep it so, it happens quickly, but we're not using too much reactants, or we're not operating at higher temperatures, or, we're implementing kind of manufacturing steps that are too expensive just in order to increase that rate of reaction. So it's all about a balance, I suppose, that you want to make sure that, of course, your reaction is proceeding, okay, and it's occurring quickly, but not too quickly that it's going to affect, say, how much we use, the temperature it's occurring at, and things, because that can also affect kind of the safety of the reaction itself, okay? Because very, very quick reactions obviously occur quite quickly, and they can be quite dangerous if they're not controlled. Okay, so it's all about a balance here. So for example, okay, so factors that can affect the rate of the reaction. The first one is definitely reactant concentrations, okay? The reason for this is that if you simply have more reactant present in a reaction, you have more particles per volume. So if I had a beaker of reactant, if that was highly concentrated, there are more reactant molecules present. So that means that's more likely that they're going to collide with one another to form our products. So what we say is that you have more frequent successful collisions between the reactant molecules because there's a higher number of them. Because of that, then the rate of the reaction increases. Okay, because you have physically more reactant present in the reaction vessel. Your temperature then is a big one. Okay, so we tend to operate kind of at higher temperatures for chemical reactions. The reason for this is that if you supply more heat to a reaction, the reactant molecules actually have more kinetic energy. Okay, so they're more mobile. They're flying around that reaction vessel at a quicker rate. Okay, so if you have a reactant molecule that's moving faster, has more kinetic energy, it's more likely to collide with other reactant molecules and form a product. So think of it this way: if you're heating it up, you're speeding up the actual reactant molecules themselves. They have more energy to kind of move around and collide. So at a higher temperature, we have a higher rate of reaction. The same then, or I suppose the opposite of that then, if you are operating at a lower temperature, so even though it's a bit safer, obviously we're not using high reaction temperatures, and so it is a safer reaction, but your rate of reaction suffers for it because the molecules don't have a lot of kinetic energy. Okay, so they're moving at a much slower pace, which means there are less collisions between the reactant molecules, or they're less likely to collide because they're moving too slow. Okay. In terms of your surface area then, so this is a big one. So if you are working with a reactant that has a greater surface area, there's actually more collision sites available for effective collisions between the reactant molecules, okay? So think of it this way, that if you had, say, a solid block, and I'm going to use salt as an example. So if we had a big chunk of salt, and if we split that in two, we're creating more collision sites on either side of that block, okay? So say this is a cube of salt, okay? So we have 1, 2, 3, 4. So we have 6 sides for effective collisions here. On this side, then we have 1, 2, 3, So we actually have 12 on this side, and then that increases further if we increase the surface area. Okay, so we're just think about the faces of that cube of salt, that if we create more faces, so we increase the surface area, there's more chance of an effective collision happening between the reactant molecules because there's more space available for them. So in that sense, the rate of the reaction increases as a result. Okay. Is everyone okay with that so far? Does anyone have any questions? All good so far?
Yes.
Okay. Perfect. So then the last two then, and this is one I mentioned during the chemical equilibrium lecture. Okay, so we use catalysts. So catalyst, and just to kind of give you a bit of a remembrance for lecture 7, so slides 21 and 22, the catalysts are substances that are added into a reaction to increase its rate. Okay, so their whole purpose of use is to increase the rate of the reaction. How they do that, okay, is that we look at what's called the activation energy of the reaction. So all reactions, no matter what it is, they have a certain activation energy. And what this is basically like an energy barrier. So for the reactant molecules to actually react with one another and form the product, think of it, they have to overcome an energy barrier to do that. So think of our A and B there, that our A reactants are reacting with one another, colliding. They have to have enough energy to almost physically bypass this barrier to form the product. So what catalysts do is that, and you'll notice between the two lines here, is that an uncatalyzed reaction is slower because it has a higher activation energy there. Okay. So less of our reactant molecules will actually overcome that barrier because it's too high. What a catalyst does is that it's added into the reaction, it will increase the rate and it won't be used up, so we can isolate it at the end. But what the catalyst actually does is that it lowers the activation energy. So it doesn't affect how much energy the reactant molecules actually have. Okay, so it's not like temperature, it won't give it more kinetic energy, but it just lowers that barrier so that they don't have to overcome such a steep barrier when a catalyst is involved. Okay, so it lowers the activation energy. More of these reactant molecules have enough energy to bypass that lowered barrier to form the product. So they're a very handy way of increasing the rate of the reaction. And because they're not used up in the reaction, some catalysts can actually be isolated from the reaction and reused. Okay, so they're much more economical, and we have more effective collisions between our reactant molecules there as a result. Okay. And finally, then your last one. So typically, what an exam question will look like is that it will most likely give you a graph to plot. Okay, so like I was talking about, you'll have your concentration and your time data. You'll be asked to plot the data itself. From there, then work out kind of your average rates of reaction, your instantaneous rates of reaction, and then they'll normally throw in a question that will challenge your knowledge on kind of the factors that affect the rate of the reaction. So it might be, say, if the temperature of this reaction was increased from 30 degrees to 60 degrees, what effect will that have on the rate of the reaction? So it's just things to look out for. That will either be like list certain number of factors that will affect a chemical reaction, or it will get more specific. So they might, like I said, they might say, well, if the temperature was increased, how would that affect the rate? If we added in more of the reactant, how would that affect it? Okay, so it's just something to keep an eye on. So your last one there then, so your pressure. So this is only for the gaseous reactions, okay? So this is very similar to what I was talking about for Le Chatelier's principle last week. So pressure will only affect the gaseous reactions. And it's just as simple as that. If you work at a higher pressure, so think of a container that's maybe a liter in size, that if you increase the pressure in that container, our reactant particles are actually in close proximity to one another. Okay, so they don't have the space to spread out around a container. That if we pressurize that system, they only have a certain amount of space to actually react in. So that means if they're in close proximity, they're much more likely to collide with one another and form a product. If you were working at low pressure, so at low pressure, if you increased, say, the size of the reaction vessel, so we went from 1 liter to 5 liters, the decrease in pressure comes from the particles have much more space to kind of spread out and fill up that new increased volume. Okay. So what happens there is that because they have more space to roam around that bigger volume, they're less likely to collide with one another, and then the rate of the reaction decreases as a result. Okay. So just for that one, it's only for gaseous reactions, and it's kind of working that if you're at a higher pressure, they have less space to react, so therefore they're more likely to bump into each other. If you're working at lower pressure, they have much more space to spread out, and they're more unlikely to collide with one another as a result. Is that okay, guys?
Yeah.
Perfect. So that is the end of the actual lecture material. Okay, so there was only, I think, maybe 7 or 8 slides in that. So what I'm going to do is, if you want to take maybe a 10-minute break now, and then I'll pull up I have a worksheet done out that kind of has different exam questions based on the rates of the reaction itself. So it'll kind of become more clear what I'm talking about and how to actually calculate it from there. Are you happy enough to do that? So we'll say if you're back maybe by, we'll say 6 o'clock, and we'll go through some of those then.
Yeah, perfect.
Okay.
Okay, perfect, guys. Thanks a million. Exam questions that I have. Is that okay?
Yeah.
Perfect. No worries. Just bear with me 2 seconds and I'll open the. Perfect. Can you guys see that Word document there? Yeah. Yeah. So you can see the practice questions.
Yeah.
Yeah.
Brilliant. Okay. So, as I was saying just before the break, all right, so what you'd normally have for these types of questions is that you would be given a table very similar to this one, all right, so this is what I was talking about here, that you have your time data and your concentration data, okay? What's really important to note is whatever SI unit is in, okay, because you could be given moles, you could be given mass, you could be given a volume, but it's the same thing each time, all right? It'll just change your SI unit at the end. But I'll get to that in a second. Okay, so but you do it in the exact same way. You don't have any of the conversions into moles to mass or mass to moles that we were doing already. You just take whatever it is that you have. All right. So a typical exam question would be a table of data. It would ask you to maybe calculate the average rate before you plot the data. Okay, so it's just taken, as I was saying during the lecture, that you take the concentration that formed at the very end over the total time of the reaction, and that's your average rate. Okay, so I'll go through that now. I'll start off with that anyway. So our question is, when an acid reacts with a metal, hydrogen is produced. Okay, so hydrogen is our product here. I wouldn't worry about this too much. The 25 centimeters cubed of 1 mole of sulfuric acid was added. It's just describing the reaction there. The most important point here is that you have your time data, so from 0 to 10 minutes, and the volume of hydrogen gas that was produced at each time. Okay, so you'll see what I was talking about there, that you'll notice that at the very start of the reaction, particularly within the first 3 minutes, that a lot of your hydrogen is formed. Okay, so that would mean that the rate of the reaction is very, very quick at the start. All right, because a lot more product is forming. You have a lot more of the reactants there at the very, very start, so they're being used up quite quickly. And that's why you have a bigger concentration of product formed. Towards the middle of the reaction, then, you'll notice that it's still increasing slightly, but not to the same extent. That's that kind of middle part of the reaction I was talking about. So you're nowhere near as steep or nowhere near as quick as at the beginning, but it's still increasing, but just not to the same extent. Okay, so your reactants are being used up, your product is still forming, but not to the same extent as it was at the start. And then you'll notice that from 8 to 10 minutes, that your reaction almost plateaus. Okay, so that was the last part of the graph I was talking about, that, you know, your reactants have all been used up. No more product can formed because you have no more reactant left. So the reaction stops. Okay, so it doesn't proceed any further because you don't have any product or reactant left over to form. All right, so taking all that into account then, so the first question was calculate the average rate of the reaction between sulfuric acid and zinc. Okay, so for your average reaction rate, this is the one I had at the start. Okay, so it's the concentration that happened at the end of the reaction versus the concentration at the start. And then you can either have the total reaction time, but I write it as the time at the end of the reaction minus the starting time. Normally for the average rate, it's just you have a starting time of 0. Okay, so you can just have your total reaction time there, but I'll write it out just so you can see it. Okay. So I'm just going to fill in everything that I have. All right. So my concentration at the end is 62 centimeters. Oh, sorry, 62 centimeters cubed. Okay. So that is the amount of hydrogen gas that was formed at the end of the reaction. And obviously the concentration at the start, the reaction didn't start, it hadn't happened yet. So I have minus 0. Okay. Can everyone see where I'm getting those values from?
Yeah.
Yeah. Okay, perfect. So the time at the end of the reaction then, so that's just your last time point or how long the reaction actually went on for. So in this case, it's 10 minutes. And then obviously then at the very start of the reaction, it hadn't happened yet. So I'm just going to put 0 minutes there. Okay, so I'm going to do a couple more of these when we're actually in our revision class as well, because it's much easier for me to kind of writing them out rather than typing. But we'll do a couple now anyway, just so you can get the gist of them. Okay, so obviously 62 minus 0 is itself. And then 10 minus 0 will give us 10 there. Okay, so then you just need to divide one by the other. So that will be 62 centimeters cubed divided by 10. So your average rate of the reaction is 6.2. And this is where it's important that we look at the SI units, okay? Because we have to include the SI unit here after everything, okay? So in this case, it will be centimeters. And then it's divided by time in minutes, okay? So your average rate of reaction will look something like this. 6.2 centimeters cubed per minute. And what that means is that over the course of this entire reaction, that on average, we formed 6.2 centimeters cubed of hydrogen gas every minute. All right. Is everyone happy enough with that so far?
Yeah.
Perfect. Okay. Okay, so the next question asked then, so it says plot the results given and comment on the shape of the graph. So what I'm going to do is I'm just going to go over to, again, not ideal, but I'm going to go over to Excel just so you can see how we plot it, okay? And I'll do a couple of these out on the board then in our revision classes. So I just copy and pasted this data over, okay? So it said to plot the concentration versus time. Okay, so I'm just going to, sorry, no. Okay, so this is our time in minutes. And this is our hydrogen gas produced, okay, in centimeters cubed. So what you would normally do is that you would, you're going to be given graph paper in the exam. So you would have to plot this using your ruler. Okay, so it's really important that for the exam itself, graph paper will be supplied to you, but just make sure you have a ruler for the exam with you. All right, but I'll remind you of all this anyway, but just because it's often forgotten. Okay. So what you do is if you're doing this in the exam, you would plot it and you would be aiming for something like this. Okay. So again, we see that nice kind of curve in the graph, okay? So as I was describing at the start, okay, a nice steep incline in the graph for the first part because our rate of reaction is quite high. A little bit of leveling off towards the middle, okay, because our reactants are being used up and the product is still forming, but not to the same rate. And then at the very end of the reaction, then no more product will form because there's no more reactant to be used up. Okay, so that's what you should be aiming for, is that really steep incline, little bit of a plateau, and then it levels off. All right. So what's really important that you note here, okay, is that your concentration should always be plotted on the x-axis. On the y-axis, I should say, sorry. So always the concentration on your y-axis, and then your time should always be on the x-axis down here. Because it will affect the shape of the graph otherwise, okay? So that's what we should be aiming for there. Is everyone okay with that so far?
Yeah.
Perfect. Okay, so I'm just going to just remind myself what time the instantaneous rate was, just 2 seconds. Okay, 2 minutes. Okay, can you guys still see the Excel, yeah? Yeah, you can still see the graph?
Yeah.
Perfect, okay. So the next question from that then, it said to plot or to calculate the instantaneous rate at 2 minutes, okay? So again, this isn't really ideal to be showing you how to do this, but just as long as you get the gist of it, and then we'll just go back over it again anyway. Okay, so what you would do is that you would have your 2 minutes. So I'm just going to highlight this. So when you're asked to calculate the instantaneous rate of a reaction at a certain time point, what I'd recommend you do is just highlight that for yourselves on the actual graph itself. Either you draw a circle around it or you highlight it just so you can see it. Okay. So say for example, we have to calculate it at 2 minutes. All right. So what you would do is you go to 2 minutes, you'd go up to the graph. No, sorry, I shouldn't. Just before I start that as well, actually. What I would do in the exam, okay. Sorry, just 2 seconds. It's a bit awkward to be doing it on Excel, but yeah, so we'd have a line graph instead. Yeah, there we go. Yeah, so we'll look something like that instead. All right. I would connect all the dots on the graph for yourself because it's going to make it easier for the tangent line. All right. Okay, so say we've plotted the graph, we've connected all the dots, we see that nice curve, and then we're asked to plot the instantaneous rate at 2 minutes. Okay, so you'd extend up from 2 minutes to the point, and then we would draw in our tangent line. Okay, so what you want to make sure is that our tangent line just hits the point there. Okay, so you don't want to kind of extend it into the graph, so it wouldn't be, if I zoom in just to show you, okay, so it wouldn't be ideal to kind of draw it like that. So even though it's hitting the point, it's kind of on top of the line itself. You want it just hitting the point. It's just much more accurate that way, okay? So if you kind of extended it in here, we're underestimating the rate of the reaction. Okay, so what you want to do is just make sure that it's hitting just above that point. Okay, I'm going to draw that in a separate color so you can see it. Is everyone okay with that so far?
Yes.
Okay. Oh, sorry, my mistake. Okay, so say we have our tangent line drawn in, all right, and I'm going to extend it just a little bit just so we can. Okay. So in this case, what I would do then, because you have to pick 2 points along the graph or along that tangent line to calculate your instantaneous rate. Okay, so what I would do is I would just highlight the end, or I should say the start. Okay, so the start and the end of that line. like that, okay? Much easier to do on graph paper, but it's just to show you. Okay, so you'll have something that looks a little bit like this. Okay. So what I would do then, because you have your 2 points highlighted there, I would connect them. So you almost end up like a triangle. Looks something like this. Okay, can everyone see where I'm getting that from? Okay, so I just pick 2 points along the tangent line. Straighten it up a little bit. Okay, so pick 2 points along the tangent line. Then I just drew 2 lines to meet that. Okay, because it's going to make it easier to see your change in the concentration and the change in time that I was talking about. Everyone okay with that so far? Yeah, you can see where I'm getting that kind of triangle shape from.
Yeah.
Okay. So now what we have to do is that we have to look at the point. So the chain, we'll mark the 2 concentrations that we picked, and then we'll look at the times. All right. So what we'll have here then is I'm just going to draw a text box just so we can label them. Just bear with me 2 seconds. Just make this a little bit easier on it. There we go. Okay, so I need to look at what concentration this point that I picked corresponds to. Okay. Now I know there's lines going all over the place, but it's just easier to kind of draw them in dashes, all right? So I'm going to extend just out from that line. Okay, so I'll change the weight just so you can see it there. Okay, so I'm going to come directly out from that point there that I picked, all right? And what that should be is, I think, approximately 62 centimeters cubed. Okay, can you see that there? So just a tick mark on the graph. So if that's like 60, 62, 64, 66, 68, 70, where I've extended that point from is roughly 62 centimeters cubed. Can everyone see that? Yeah, you can see where I'm getting that value from?
Yeah.
Perfect. So that's what I'm just going to, I'll just write that over here. Okay, so we have 60, 62 at the start of the line. Okay. Okay, so I'm going to do the very same thing then for my value down here. Okay, so I'm just going to come out to meet the graph there. Okay, so roughly then that should be 28. Okay, so I'm just coming out to meet that line, and that's corresponding to a concentration of around 28 centimeters cubed. Everyone happy enough with that so far, yeah?
Yes.
Okay. So there's my 2 concentrations. Okay, so now I just need to look at the times where that happened. Okay, so I know there's kind of lines going all over the place, but we'll try and stick with it. Let me just. Okay, so I've marked my point in the graph, and now I'm going to extend that all the way down to meet my x-axis. So it might be handy for you on the day, guys, is that if you have, for the exam, if you have kind of a couple of different color pens, that you're not getting too confused where the tangent line is and where you're kind of coming out to meet the graph. Just to make it a little bit easier on yourselves. But for now, I'm just going to put it in different color here. Okay. So we have our 2 parts. Yeah, because on graph paper it's just it's much easier to do. Okay, so roughly then, like very roughly, we'll say that that point there corresponds to about 62 centimeters cubed. If we drop it down to the other axis, it's about 3.2 minutes. Okay, so just extending that line all the way down, it's roughly 3.2 minutes. And then we'll do the exact same then for my other side. Okay, so we'll come up to meet the graph there, just drop it all the way down. Okay, so roughly then I'd say that's about 0.8. Okay, so just dropping it all the way down to meet the x-axis. So approximately 0.8 minutes. All right. Is everyone okay with that, guys?
Yeah.
Yeah.
Perfect. So what I'll do is just to remind you, hold on now. So I'm just going to jump back onto my presentation. Okay, can you see the presentation now?
No.
Okay. Can you see it now?
Yeah.
Okay, perfect. So we're looking at this value here, or this equation, I should say. All right, so we've labeled our concentrations and at the start and the end of the line. So we have those from the graph, and we also have the times. So we just need to input this, all of the data that we just got into that equation, and we should be able to calculate the instantaneous rate from that. Okay, so I'm going to jump back over then to my Excel there. Okay. So from what I just said, all right, so we have our concentration at the start of the line. So that is going to be our 62 centimeters cubed. The concentration at the end of the line then is our 28. Our time at the start of the line then is 3.2. And I'm going to minus then our time at the end of the line, which is 0.8. All right, so it should tidy up to something like this. Our concentration at the start of the line minus the concentration at the end of the line, so our two values there. And then our times at the start and the end of the line, so 3.2 and 0.8. So all in all then we should be getting an instantaneous rate of 14.16. Okay. So where we actually answer that then, sorry guys, I know jumping back and forth between different things. Okay, so we have our average rate, we calculated that. So we said find the instantaneous rate at 2 minutes. So from plotting the graph and doing that on Excel, we should have 14.16 centimeters per minute. All right, and that's our value for that one. And you'll notice then that kind of ties into what I was saying at the very start, okay, that your average will give you a broad overview or an estimation of how quickly that reaction happens, taking every stage into account. Okay, so as you can see, it's quite lower in comparison to your instantaneous rate, okay, because it's given a broad overview of the whole reaction. Whereas your instantaneous rate at 2 minutes, it's happening nearly at the very start of that reaction. Okay. So you would expect it to be a lot higher at that point because, like I said, your reactions are there in abundance. They're reacting very, very well. A lot of product is forming. A lot of reactants are being used up. So you would definitely expect it to be higher at the start of the reaction in comparison to what it was overall. Okay. Are you happy enough with that, guys? Can everyone see where I got those values from? Okay. So your last question then would be, so it would tie in something like this, okay? And that's what I was mentioning there a while ago, that you would typically calculate the average rate, plot your data that you're given, find the instantaneous rate based on that tangent, and then they would throw in something like this. Okay, so it says, what changes would you expect if 25 centimeters cubed of 0.5 molar H2SO4 were used in the system? Okay. So if we look at what we were given at the very start there, we were told that we used 1 mil of sulfuric acid. All right. If we were, so that was the rate of reaction if we used 1 molar. So coming all the way down here, if we had to repeat that reaction again, and we used a sulfuric acid that was half the concentration of our first sulfuric acid, what would you expect the rate of the what would happen the rate of the reaction? Does anyone know? So think about the factors that affect it.
You wouldn't get as much product.
Yeah, absolutely. You wouldn't get as much product, and the rate of the reaction would actually slow down. Okay, because our sulfuric acid is the reactant in that case. Okay, so if we did this experiment with 1 molar sulfuric acid, we have a much more concentrated solution there. Okay, so we have a lot more reactant there in order to react. So it's going to happen much more quickly. If we repeated that experiment and used a more dilute version, okay, so your 0.5 molar, it's much more dilute. We don't have as much reactant as we did at the start. So we wouldn't expect it to happen at the same rate. It would be a decreased rate of reaction in comparison. Okay. Can everyone see where I'm getting that comparison from? Yeah. So look, if you look at 1 molar sulfuric acid, it's double the concentration of our 0.5 molar here. Does that make sense?
Yeah.
Yep.
Perfect. Okay. So guys, what I might do, I'm just looking at the questions that I have on the rest of the worksheet. Now, this worksheet is up on Moodle if you kind of want to give them a go yourselves throughout the week, all right? But just looking at kind of what you'd have to do, they're very, very similar, okay? But I might leave these until our revision class because it's much easier to draw them out on graph paper and actually show you how you'll do it in the exam rather than using Excel. But I just wanted to show you just so you'd have an idea of how to do it. But I think I might save these questions until our revision class because it'll become a lot more clear when you actually see the graph paper in front of you. Is that okay?
Yep.
Perfect, guys. So if that's the case, then that's everything. So I'm going to stop sharing the screen. Just bear with me 2 seconds.